March 24, 1999. Whiteman Air Force Base, Missouri. Two pilots climbed into the cockpit of a B-2 Spirit bomber as darkness settled over the continental United States. Their mission briefing had been clear and unprecedented. Fly 14 hours across the Atlantic Ocean, penetrate the most fortified airspace in Europe, destroy high-value targets inside Yugoslavia, and return home without fighter escort, without electronic warfare support, and without leaving a trace on enemy radar screens. Major Tom Bussiere settled into the right seat as mission commander, his co-pilot to the left. Behind them, in the twin weapons bays carved deep into the flying wing's belly, sat 16 GPS-guided joint direct attack munitions. Each bomb weighed 2,000 pounds. Each had been programmed with precise coordinates of Serbian military installations that NATO intelligence had designated as critical nodes in Slobodan Milosevic's command structure. As the B-2 rolled down the runway and lifted into the night, its four General Electric F-118 turbofan engines producing 69,000 pounds of thrust, the aircraft began a journey that would validate 3 decades of classified research, billions of dollars in development costs, and a revolutionary premise that had once seemed impossible. That a bomber with a wingspan larger than a 747 could become functionally invisible to the most sophisticated air defense networks on Earth. The Yugoslav military had prepared for this moment. Following the collapse of the Soviet Union, Serbia had inherited one of the densest integrated air defense systems outside of Moscow itself. Soviet-designed SA-2, SA-3, and SA-6 surface-to-air missile batteries ringed Belgrade and every strategic facility in the country. Early warning radars swept the skies continuously, overlapping their coverage to eliminate blind spots. Fighter squadrons flying MiG-29 Fulcrums stood on strip alert, ready to scramble within minutes. The commanders of the Ratno Vazduhoplovstvo I Protivzdusna Odbrana, the Yugoslav Air Force and Air Defense, had studied NATO tactics during the Gulf War. They knew stealth aircraft existed. They had watched F-117 Nighthawk strike Baghdad with impunity in 1991. But they also believed, with absolute confidence, that their updated radar systems, their disciplined crews, and their tactical adaptations would allow them to detect, track, and destroy any aircraft that dared to violate their airspace. Serbian Air Defense Chief Colonel Zoltan Dani would later recall the prevailing attitude among his commanders in those early days of Operation Allied Force. We knew the Americans had technology, but we also knew that every aircraft, no matter how advanced, must eventually reveal itself. When the bomb bay opens, when the weapons release, when the aircraft maneuvers, at that moment physics cannot be cheated. At that moment we would see them. Yet as the B-2 crossed into European airspace, descended to its operational altitude, and began its approach toward Yugoslav territory, every assumption undergirding that confidence began to collapse. The aircraft that Serbian radar operators expected to see a target return corresponding to a large bomber, something comparable to a B-52 or even a tactical fighter, simply did not appear on their scopes. What they did not understand, what they could not have understood without access to the most classified engineering documents held by the United States Air Force and Northrop Grumman Corporation, was that the B-2 Spirit possessed a radar cross-section approximately 1/10,000th the size of a conventional bomber. Official estimates, declassified years after Operation Allied Force, placed the B-2's RCS at roughly 0.1 square meters when viewed from the most favorable angle, comparable to a large bird, perhaps a goose in flight. From less favorable aspects, the signature could shrink even further to dimensions smaller than a golf ball. This was not merely a reduction in detectability. This was effective radar invisibility achieved through a combination of aerodynamic shaping, materials science, and electromagnetic theory that represented the absolute cutting edge of late Cold War aerospace engineering. The B-2's stealth characteristics began with its fundamental architecture. Traditional aircraft present dozens of surfaces and angles that reflect radar energy back toward the transmitting antenna: vertical stabilizers, engine nacelles, wing fuselage junctions, weapons pylons, antennas. Each of these features creates a distinct radar return. The B-2 eliminated nearly all of them. Its flying wing configuration, spanning 172 feet from tip to tip but only 17 feet high, was a continuous blended surface with no vertical control surfaces. No protruding tail, no external weapons hardpoints. Every line, every curve had been calculated using supercomputers running computational fluid dynamics models that predicted how electromagnetic radiation would interact with the aircraft's shape. Where earlier stealth designs like the F-117 Nighthawk had relied on faceted flat panels, angular surfaces designed to reflect radar energy away from the source but creating sharp detectable edges, the B-2 employed a technique called continuous curvature. Its skin flowed in smooth, mathematically optimized contours that gently redirected radar waves in every direction except back toward the receiver. The effect was not to absorb radar energy, but to scatter it so diffusely that no single return was strong enough to register as a target. But shape alone could not achieve the level of invisibility the B-2 demonstrated over Yugoslavia. The aircraft's outer skin was a marvel of materials engineering that remained partially classified decades after its first flight. The primary structure consisted of carbon graphite composite materials mixed with titanium, substances chosen not only for their strength-to-weight ratio but for their electromagnetic properties. Carbon composites are inherently non-reflective to radar frequencies. Unlike metal, they do not efficiently conduct electromagnetic radiation. Over this composite substrate, Northrop engineers applied multiple layers of radar-absorbent material. The precise chemical composition of these RAM coatings has never been fully disclosed, but unclassified reports indicate they contain microscopic particles of carbonyl iron or ferrite suspended in a polymer matrix. When radar waves struck these coatings, they induced molecular oscillations in the metallic particles, converting electromagnetic energy into heat that dissipated harmlessly into the atmosphere. The coatings were not uniform across the aircraft. Leading edges, engine intakes, weapons bay doors, any surface that might generate a strong radar return received specialized applications. The intake structures, which could not be eliminated entirely because the engines required air, were treated with the most advanced absorbent materials available and shaped to channel radar energy deep into the engine nacelles, where it would be trapped and absorbed rather than reflected back outward. Even the aircraft's engines contributed to its stealth profile. The four F-118G100 turbofans, each producing 17,300 pounds of thrust, were buried deep within the wing structure. Their exhaust was not expelled through conventional circular nozzles, which create intense infrared signatures visible to heat-seeking missiles. Instead, the B-2's exhaust ports were flattened, slot-shaped openings on the upper surface of the wing, positioned so that the hot gases mixed rapidly with cool ambient air and were shielded from ground-based infrared sensors by the wing itself. The engine faces, normally a bright radar reflector on conventional aircraft, were completely hidden behind serpentine intake ducts lined with RAM. No radar wave entering those intakes had a direct line of sight to the compressor blades. Acoustic signature, another detection vector, was minimized by the engine placement and by the subsonic operating speeds the B-2 maintained during its penetration phase. Unlike supersonic fighters that announced their presence with sonic booms and roaring afterburners, the B-2 ghosted through the sky at high subsonic speeds, its passage marked by nothing more than a faint whisper audible only at very close range. On the night of March 24, as the B-2 entered hostile airspace, Major Bussière engaged what pilots called full stealth configuration. This involved a series of classified procedures referred to internally as stealthing up, adjustments to the aircraft systems and flight profile that maximized its low observable characteristics. The cockpit lights dimmed to complete darkness to prevent any light from reflecting off the canopy. Specific radar reflective panels and access hatches were checked to ensure perfect sealing. The aircraft's own AN/APQ-181 synthetic aperture radar, capable of creating photographic-quality terrain maps, operated in a low probability of intercept mode, using frequency hopping and low-power emissions that enemy ELINT stations could not distinguish from background radio noise. The B-2 maintained strict radio silence. No communications, no transponder signals, no electronic emissions of any kind except for the passive reception of GPS navigation data. To Serbian radar operators scanning their screens that night, the airspace appeared empty. Their equipment functioned normally. Returns from civilian airliners over Italy and Austria appeared as expected. NATO support aircraft, AWACS controllers, tankers, electronic warfare platforms were clearly visible operating in safe areas over the Adriatic Sea in Bosnia. But of the B-2 there was nothing. No primary radar return, no secondary IFF signal, no radio chatter. It was as if the aircraft did not exist. Yet the B-2 was there, closing on Belgrade at an altitude above 40,000 feet, well above the effective ceiling of most Serbian surface-to-air missiles. The targeting data had been uploaded before takeoff, but the crew continuously refined their approach using the aircraft's sophisticated navigation systems. The B-2 carried an inertial navigation system accurate to within meters over intercontinental distances, augmented by GPS receivers that provided real-time position updates. As the bomber reached its initial point, the weapon system activated. The two rotary launchers in the bomb bays began positioning the first set of JDAMs for release. Each JDAM consisted of a standard Mark 84 2,000-pound bomb fitted with a guidance kit containing GPS receivers, an inertial measurement unit, and movable tail fins. Once released, the bomb would glide toward its target, making continuous adjustments to its trajectory based on GPS coordinates, able to strike within 13 meters of the aim point even when released from high altitude through clouds and darkness. The target for this first pass was a command and control bunker near Belgrade, a hardened facility from which Yugoslav military leadership coordinated their air defense network. At 0237 local time, the bomb bay doors opened. For 17 seconds, as the rotary launcher positioned and released the weapons, the B-2's radar cross-section increased dramatically. The open weapons bay created a cavity that trapped and reflected radar energy, temporarily transforming the aircraft from a barely detectable phantom into something that might register on enemy scopes. Serbian doctrine called for continuous radar sweeps of known attack corridors. If their operators had been scanning the right sector at the right moment with the right radar frequency, they might have detected something, a brief, anomalous return, a flicker on the screen that appeared and vanished before it could be confirmed. But in the chaos of the first night of war, with hundreds of NATO aircraft operating across the region, with radars being jammed by electronic warfare platforms, with missile batteries forced to shut down their transmitters within seconds to avoid being targeted by anti-radiation missiles, that 17-second window passed unnoticed. The JDAMs fell away, their GPS guidance systems locked onto coordinates, their control surfaces already adjusting trajectory. The bomb bay doors closed. The B-2 returned to its lowest observable state and turned away from the target area, beginning the long journey back across the Atlantic to Missouri. 30 seconds later, the first bomb detonated. The reinforced concrete roof of the command bunker ruptured under the precision strike. Secondary explosions followed as penetrator warheads designed to defeat hardened structures drove through multiple levels before detonating inside the facility. Communications circuits went dead. Backup power failed. The facility, which had been a critical node linking air defense batteries across the Belgrade region, ceased to function. Serbian commanders, expecting NATO to open the campaign with cruise missile strikes followed by conventional bombing runs over the following nights, suddenly faced a strategic paralysis. High-value targets were being destroyed by an enemy they could not see, could not track, and could not engage. The psychological impact was immediate and profound. Air defense crews stared at their radar screens with growing frustration. Their equipment showed empty sky. Their missile batteries remained on alert, unable to acquire targets, yet the explosions continued. Night after night, installations that should have been protected by overlapping radar coverage and multiple missile batteries were obliterated with surgical precision. If you appreciate discovering the classified technologies that redefine modern warfare, consider subscribing to Classified Warfare for deeper investigations into the systems that decided the outcome before the first shot was fired. The full scope of the B-2's role in Operation Allied Force would not become clear until after the 78-day campaign concluded. The United States Air Force initially deployed just 6 B-2 bombers to the conflict, a tiny fraction of NATO's total air assets. These 6 aircraft flew only 49 sorties, less than 1% of all combat missions during the operation. Yet those 49 sorties delivered 656 JDAMs, representing 11% of all the bombs dropped during Allied force. More significantly, the B-2s were assigned the most heavily defended targets: command bunkers, communications facilities, political leadership compounds, integrated air defense nodes. Targets that conventional aircraft could not strike without unacceptable risk. Targets that cruise missiles, with their hours-long flight times and predictable trajectories, might not be able to penetrate before the target relocated or erected additional defenses. The B-2 could reach these targets within hours of receiving orders, strike with precision that placed 90% of its weapons within 40 feet of the designated impact point, and return to base without ever entering the engagement envelope of Serbian air defenses. The evidence of this effectiveness came not just from post-strike reconnaissance, but from the increasingly desperate adaptations attempted by Yugoslav forces. Colonel Zoltan Dani, commander of the 250th Air Defense Missile Brigade, later described the strategic frustration his units experienced. "We understood that NATO had aircraft operating above us. We could hear them being refueled over the Adriatic. Our Elant operators intercepted radio communications between bomber crews and air traffic control stations as they entered European airspace. We knew they were coming, but once they crossed into our territory, they vanished. Our SA-2 and SA-3 systems, which had been optimized to detect high-altitude bombers during the Cold War, showed nothing. Our SA-6 systems designed for lower altitudes were equally blind. We attempted to use long-wavelength early warning radars, thinking perhaps the lower frequency might generate some return from these stealth aircraft, but the signature was so weak and intermittent that we could not generate a targeting solution. We could not launch missiles at ghosts. Danny's unit achieved one significant success during Allied force, but it was a success that paradoxically highlighted the effectiveness of the B-2 stealth technology. On March 27, 1999, just 3 days after the campaign began, a Yugoslav SA-3 battery under Danny's command shot down an F-117 Nighthawk stealth fighter. The shootdown occurred because the F-117, operating at medium altitude on a predictable flight path, opened its bomb bay doors directly over the SA-3 site. For a handful of seconds, the increased radar cross-section was sufficient for the Serbian crew to achieve lock and launch. The F-117 pilot, Lieutenant Colonel Dale Zelko, ejected safely and was recovered by NATO forces. The loss of the F-117 sent shockwaves through the Pentagon. If older stealth technology could be defeated by a 1960s-era Soviet missile system operated with discipline and ingenuity, what did that mean for the vulnerability of other stealth platforms? The answer came in the remaining 75 days of the war. Not a single B-2 was shot down, not one was damaged. Not one was even successfully tracked from weapons release to exit from hostile airspace. The difference lay in the generational leap in stealth technology that separated the F-117, designed in the late 1970s using flat-faceted surfaces, from the B-2, designed in the 1980s using continuous curvature and advanced materials that the earlier aircraft could never incorporate. Yugoslav forces tried everything. They modified their radar operating procedures, keeping transmitters active for only seconds at a time to avoid targeting by NATO anti-radiation missiles, hoping to catch fleeting glimpses of stealth aircraft. They deployed observers with passive infrared sensors attempting to detect the heat signatures of approaching bombers. They studied the timing of attacks, noting that the B-2s operated exclusively at night and appeared to strike targets in northern Serbia above the 44th parallel. Intelligence officers plotted probable approach routes and requested fighter patrols along those corridors. None of it worked. The MiG-29 pilots, constrained by fuel limitations and constantly harassed by NATO fighters with superior beyond visual range missiles, never made contact with a B-2. Ground observers, scanning the night sky with infrared binoculars, saw nothing. The B-2's exhaust management system and high-altitude operation made it effectively invisible in the infrared spectrum from ground level. Electronic intelligence units monitoring radio frequencies could sometimes detect when B-2s were operating in the theater based on indirect indicators. Changes in NATO air traffic patterns, increased activity among tanker aircraft, coded communications between U.S. command centers. But this intelligence was useless for air defense purposes. Knowing that a B-2 was somewhere over Serbia did not provide a target for missiles or fighters. The technical sophistication of the B-2 extended far beyond its stealth characteristics. Each aircraft cost approximately $2.1 billion, making it the most expensive military aircraft ever produced. That cost reflected not just the exotic materials and computational design work, but the extreme precision required in manufacturing. The continuous curvature surfaces had to be fabricated to tolerances measured in thousandths of an inch. The ram coatings had to be applied in climate-controlled facilities with exact thickness specifications. Even minor imperfections, a poorly fitted access panel, a scraped section of coating, a structural repair using non-approved materials could create a radar hot spot that compromised the entire aircraft's stealth profile. Maintenance requirements were extraordinary. After every flight, technicians inspected the ram coatings for damage. Environmental factors, rain, hail, extreme temperature variations, even prolonged sun exposure could degrade the materials. The B-2 required specialized hangars maintained at specific temperature and humidity levels. When deployed overseas, Air Force engineers built climate-controlled shelters to protect the aircraft between missions. During Operation Allied Force, B-2s flew directly from Whiteman Air Force Base in Missouri to their targets and back, round-trip missions lasting up to 30 hours, specifically to avoid the maintenance complications of deploying to forward bases in Europe. The crew workload during these marathon missions was intense. The B-2 had a crew of just 2 pilots compared to 4 on the B-1B and 5 on the B-52. There was no relief crew, no dedicated navigator, no bombardier. The left seat pilot handled flying duties, while the right seat mission commander managed weapons systems, navigation updates, and threat assessment. Both crew members wore specialized flight suits with provisions for waste management during the 30-plus-hour missions. They consumed prepackaged meals, took turns napping in short cycles to maintain alertness, and managed fatigue through carefully timed use of caffeine and prescribed medications. The cockpit environment was designed for endurance. Seats with advanced ergonomics, environmental systems maintaining optimal temperature and humidity, multifunction displays that reduced eye strain. Yet even with these accommodations, the physical and mental demands of flying a 14-hour mission into hostile territory, executing weapons release with split-second precision, and returning across the Atlantic pushed crews to their limits. Major Bussière later recalled that the most challenging aspect was not fear of being shot down. He trusted the aircraft's stealth capabilities, but rather the sustained concentration required to maintain situational awareness for such extended periods while knowing that a single error in navigation, a single system's malfunction, could compromise the mission. The strategic implications of the B-2's performance in Yugoslavia reverberated far beyond the Balkans. For military planners in Moscow, Beijing, and Tehran, the lessons were stark and unambiguous. The Soviet-derived integrated air defense systems that had been considered impenetrable during the Cold War were now functionally obsolete against stealth technology. Surface-to-air missiles that could not acquire their targets were useless. Fighters that could not be vectored to intercept points were irrelevant. Radar networks that transmitted into empty sky might as well have been shut down. The strategic calculus of air defense had fundamentally changed. During the Cold War, the Soviet Union had invested enormous resources in developing layered air defense systems specifically to counter American bomber fleets. The S-75, S-125, and S-200 missile systems, the MiG-25 and MiG-31 interceptors, the network of ground-controlled intercept stations, all were designed around the assumption that incoming bombers would be detectable and trackable, that engagement opportunities would exist, that attrition could be imposed even if not every bomber was stopped. The B-2 invalidated that entire strategic framework. A bomber that cannot be detected cannot be intercepted. A bomber that cannot be intercepted cannot be stopped. A bomber that cannot be stopped renders defensive investment meaningless. Russia responded by accelerating research into counter-stealth radar systems. Engineers explored lower-frequency radars, arguing that longer wavelengths might generate detectable returns from stealth aircraft even if they could not provide the precision needed for targeting. Bistatic and multistatic radar configurations were tested, using separated transmitters and receivers to detect stealth aircraft by the radar energy they scatter in directions other than back toward the source. These systems showed promise in experimental conditions, but they faced fundamental limitations. Low-frequency radars have poor resolution, making it difficult to distinguish individual targets or generate firing solutions accurate enough for modern missiles. Bistatic systems require extensive geographical deployment, precise timing synchronization, and are vulnerable to electronic countermeasures. More critically, they are reactive solutions, attempting to compensate for a technological advantage that the United States had spent 3 decades and hundreds of billions of dollars developing. The gap was not one that could be closed quickly or cheaply. China, observing Yugoslavia's impotence against NATO stealth operations, redirected substantial resources toward its own stealth programs. The results would not appear for decades, emerging as the J-20 fighter program in the 2010s. But even as nations struggled to develop counter-stealth technologies, the United States was already working on the next generation. The B-2's operational profile during Allied force demonstrated capabilities that went beyond simple stealth. The aircraft's unrefueled range of 6,000 nautical miles could be extended indefinitely through aerial refueling, giving it true global reach. A B-2 could strike any target on Earth within hours, operating from a single main operating base in the continental United States. This eliminated the need for forward-deployed bases, with all the logistical complications, host nation political considerations, and vulnerability to preemptive strikes that such bases entailed. The weapons systems integration allowed the B-2 to employ both conventional and nuclear munitions. While Allied force saw only conventional JDAMs deployed, the B-2's primary mission during the Cold War had been nuclear penetration of Soviet airspace. Each aircraft could carry 16 B-83 nuclear bombs, each with a yield of up to 1.2 megatons, sufficient to destroy any hardened target on Earth. The combination of stealth characteristics, global range, and nuclear payload made the B-2 the ultimate strategic deterrent. an aircraft that could, in theory, penetrate Russian or Chinese airspace without warning, destroy command and control facilities, leadership bunkers, and strategic weapons storage sites, and return to base before effective retaliation could be organized. The deterrent value lay not in whether such a mission would succeed, though Air Force planning documents suggested high confidence, but in the absolute uncertainty it imposed on adversary planning. How do you defend against an attack you cannot detect until the weapons detonate? The psychological dimension of stealth warfare emerged as a significant factor during and after Operation Allied Force. Serbian forces, despite never successfully engaging a B-2, lived under constant fear of attack. Every night brought the possibility of precision strikes against any target. Command facilities had to relocate frequently. Leadership spent nights in dispersed locations rather than in protected bunkers that might be targeted. Air defense batteries were forced to limit radar emissions, reducing their effectiveness against conventional aircraft in order to avoid revealing their positions to anti-radiation missiles that might be carried by unseen stealth bombers. The inability to defend against B-2 attacks created a sense of helplessness that corroded morale and complicated military operations. Intercepted communications from Yugoslav forces during the campaign revealed growing frustration and fatalism. One air defense commander in a radio transmission recorded by NATO SIGINT assets expressed the prevailing sentiment: "We are firing at ghosts while they destroy us at will. Our missiles sit unused because we have no targets. Our fighters burn fuel searching for aircraft they will never find. This is not warfare, this is execution." The psychological impact extended to political leadership. Milosevic, confident in his military's ability to inflict casualties on NATO forces and thereby break the alliance's resolve, found instead that his most critical facilities were being systematically dismantled without his forces achieving any successful counterstrike. The political calculus that had led him to defy NATO demands quickly deteriorated, as it became clear that the alliance could sustain operations indefinitely without significant losses, while Serbian military capabilities eroded night after night. The post-war analysis conducted by the United States Air Force documented effects that exceeded even optimistic pre-war projections. Lieutenant General Michael Short, commander of NATO's air component during Allied force, stated in his after-action report that he quickly came to expect 16 quality designated mean points of impact from each B-2 mission, in other words, 16 successful target destructions per sortie. This level of effectiveness was unprecedented in the history of aerial bombardment. During World War II, it often required hundreds of bomber sorties to destroy a single hardened target, with massive collateral damage and significant aircraft losses. During Vietnam, precision-guided weapons improved accuracy, but aircraft still faced substantial air defense threats. The B-2 combined near-perfect weapons accuracy with complete invulnerability to defensive systems. The result was a strategic capability that fundamentally altered the relationship between air power and ground warfare. Targets that had once required extensive suppression of enemy air defenses, multiple waves of strikes, and acceptance of losses could now be destroyed by a single B-2 flying alone through the heart of enemy territory. Yet the B-2 program was not without controversy and limitations. The original plan called for 132 aircraft, sufficient to provide continuous global coverage and deep penetration capability against the Soviet Union. Budget constraints, exacerbated by the collapse of the USSR and the resulting peace dividend expectations, reduced procurement to just 21 aircraft. One of these was lost in a 2008 crash at Andersen Air Force Base in Guam, caused by moisture contamination of air data sensors. This left the Air Force with 20 operational B-2s, a fleet so small that only 6 to 10 aircraft were typically mission-ready at any given time due to the intensive maintenance requirements. The cost per flight hour exceeded $130,000, making the B-2 by far the most expensive aircraft to operate in the American inventory. Each aircraft required approximately 120 hours of maintenance for every hour of flight time, much of it dedicated to inspecting and repairing the RAM coatings. The climate-controlled hangar requirements meant that B-2s could only be permanently based at Whiteman Air Force Base, which had the specialized facilities needed to support the fleet. Forward deployments were possible but complicated, requiring the construction of temporary climate-controlled shelters and the deployment of specialized maintenance teams. The materiel limitations raised questions about sustainability in a prolonged conflict. 20 aircraft, even operated with maximum efficiency, could only strike a finite number of targets per day. In Operation Allied Force, B-2s flew approximately one sortie per day, limited by crew rest requirements and maintenance intervals. Against Yugoslavia, a small nation with a limited target set, this was sufficient. But in a hypothetical conflict against a peer adversary like Russia or China, with hundreds or thousands of high-value targets distributed across continental expanses, 20 B-2s would be insufficient to achieve strategic effects within operationally relevant timelines. Air Force planners recognized this limitation and in the early 2000s began development of the Long-Range Strike Bomber program, later designated the B-21 Raider. This next-generation stealth bomber, built by the same Northrop Grumman team that created the B-2, incorporates advances in materials science, manufacturing techniques, and systems integration developed over the intervening decades. The B-21 is designed to be more maintainable, with radar-absorbent materials integrated into the structure rather than applied as coatings, reducing the maintenance burden. It is planned for procurement in larger numbers, with initial plans calling for at least 100 aircraft. But even with the B-21 program underway, the Air Force has continued to upgrade its B-2 fleet to maintain relevance until the new bomber achieves full operational capability. Modernization efforts for the B-2 have focused on expanding its weapons compatibility and enhancing its ability to operate in GPS-denied or degraded environments. Early in its service life, the B-2 was limited to carrying unguided gravity bombs and JDAMs. Subsequent upgrades integrated the GBU-37 GPS-aided munition, a 5,000-pound penetrator designed to destroy deeply buried bunkers, and the massive ordnance penetrator, a 30,000-pound bunker buster capable of defeating any hardened structure on Earth. The integration of the AGM-158 Joint Air-to-Surface Standoff missile provided the B-2 with a cruise missile capability, allowing it to strike targets from outside the range of even advanced air defense systems. Recent modifications have added radar-based targeting modes that allow the B-2 to employ precision weapons even when GPS signals are jammed or spoofed by adversary electronic warfare systems. Communications upgrades provide secure, jam-resistant satellite links compatible with NATO systems, enabling the B-2 to receive in-flight retasking orders and coordinate with other allied assets. These enhancements ensure that the B-2 remains a credible penetrating strike asset even as potential adversaries develop more sophisticated countermeasures. The question of counter-stealth technologies continues to drive innovation in air defense systems. Russian firms have marketed the Nebo-M radar system, a multi-band complex that combines VHF, L-band, and X-band radars to detect stealth aircraft, by exploiting the fact that different radar frequencies interact differently with radar-absorbent materials and aircraft geometry. Chinese researchers have published papers on quantum radar concepts that theoretically could detect stealth aircraft through quantum entanglement effects, though practical implementation remains speculative. Infrared search and track systems have improved dramatically since the 1990s, offering potential detection methods that bypass radar stealth entirely. Yet none of these systems has been proven in combat and all face fundamental physical and operational limitations. Low-frequency radars, while potentially able to detect stealth aircraft, cannot provide the precision needed to guide weapons. The radar returns are too diffuse, the resolution too poor. At best, they might provide early warning that a stealth aircraft is operating somewhere in a large area, information of limited tactical utility. IRST systems require relatively close range and are degraded by weather, haze, and the tendency of high-flying aircraft to be obscured by cloud layers. Even if detection is achieved, the challenge of passing targeting information to weapon systems in real time, particularly when the stealth aircraft is actively jamming and maneuvering, remains formidable. The enduring advantage of stealth technology, as demonstrated by the B-2's performance over Yugoslavia, lies in the operational tempo it enables. A bomber that can operate independently without suppression of enemy air defenses, without fighter escort, without electronic warfare support, can strike with minimal planning time and maximum surprise. Conventional strike packages require coordination among dozens of aircraft. Fighters to sweep enemy interceptors, electronic warfare aircraft to jam radars, suppression of enemy air defense platforms to destroy SAM sites, tankers to refuel aircraft, AWACS to coordinate the package. Assembling such a package takes hours and requires deconflicting complex airspace, timing issues, and rules of engagement. The B-2 eliminates this complexity. A single bomber can be launched on short notice, refueled in flight over safe territory, and strike its target without relying on supporting assets. This responsiveness was critical during Allied force when emerging intelligence sometimes identified high-value targets with only hours of warning. By the time a conventional strike package could be organized, the target might have relocated. The B-2 could be retasked in flight and strike the target before it moved. The operational concept demonstrated over Yugoslavia has become the foundation for American strategic bombing doctrine in the 21st century. During Operation Enduring Freedom in Afghanistan, B-2s flew some of the longest combat missions in aviation history, launching from Whiteman, striking targets in Afghanistan, and returning to Missouri in missions exceeding 40 hours. During Operation Iraqi Freedom, B-2s opened the campaign with precision strikes against Iraqi leadership facilities, attempting to decapitate the regime with surgical attacks that minimized collateral damage. In the 2011 intervention in Libya, B-2s struck hardened aircraft shelters and air defense sites in the opening hours of operations, clearing the way for conventional aircraft. In each case, the pattern established over Yugoslavia repeated, stealth bombers conducting deep penetration strikes against the most heavily defended targets, operating with impunity, achieving strategic effects disproportionate to their small numbers. The intelligence value of the B-2 program extends beyond its operational missions. The mere existence of a fleet of stealth bombers capable of striking any target on Earth with minimal warning has reshaped adversary strategic planning. Russian and Chinese military leadership cannot assume that critical facilities, command bunkers, strategic weapons storage sites, leadership compounds, are safe from attack even in peacetime. This uncertainty complicates crisis planning and constrains escalation options. During a crisis, leaders must consider that facilities they believe are secure might be destroyed without warning if conflict erupts. This introduces a use it or lose it dynamic that can paradoxically increase incentives for preemptive action, a strategic instability that arms control theorists have warned about. Yet it also imposes caution, because leaders know that even successful preemptive strikes against forward-deployed U.S. forces will not eliminate the B-2 fleet based in Missouri, which could conduct immediate retaliatory strikes against homeland targets. The deterrent value lies in this survivability and responsiveness, the credible threat that aggression will be met with strategic punishment that cannot be prevented by defensive measures. The technical methods by which the B-2 achieved its stealth characteristics remained partially classified for decades after its introduction, but a combination of declassification efforts, published research, and analysis of fragments from the downed F-117 in Yugoslavia has revealed many details. The continuous curvature shaping was made possible by advances in computational fluid dynamics software developed in the 1980s, specifically for the Advanced Technology Bomber program. Engineers used Cray supercomputers to model radar returns from thousands of different surface configurations, iteratively optimizing the design to minimize signature across multiple radar frequency bands and aspect angles. This computational approach was revolutionary. Previous aircraft designs had been optimized for aerodynamic performance, with stealth considerations added later as compromises. The B-2 was designed from the beginning as a stealth platform, with every other characteristic aerodynamics, structural strength, payload capacity engineered around the requirement for minimum radar signature. The result was an aircraft that looked unlike anything that had flown before, a shape that seemed almost organic, sculpted by algorithmic processes rather than traditional aeronautical engineering. The manufacturing processes required to build the B-2 were equally unprecedented. The continuous curvature surfaces had to be fabricated from composite materials, laid up in specific orientations to manage both structural loads and electromagnetic properties. Northrop developed specialized autoclaves large enough to cure entire wing sections, facilities that did not exist when the program began. The RAM coatings were applied in dust-free clean rooms with precise control over temperature, humidity, and application thickness. Workers wore specialized protective equipment because some of the materials used in the coatings were toxic. Every panel, every fastener, every access door had to be fitted with tolerances measured in thousandths of an inch to avoid creating radar reflections at panel gaps. The production process for a single aircraft took years, with multiple inspection points where electromagnetic testing verified that the stealth characteristics met specifications. If a section failed testing, it had to be disassembled and reworked, adding months to the schedule. The complexity and precision required drove costs to levels that became politically unsustainable, ultimately limiting production to 21 aircraft. Yet those 21 aircraft achieved their strategic purpose. On the final night of Operation Allied Force, June 10, 1999, After Milosevic had agreed to NATO's terms and ordered Yugoslav forces to withdraw from Kosovo, a Serbian military analyst published an essay that circulated among defense professionals in the years that followed. The analyst, writing under a pseudonym, reflected on the lessons of the campaign. We understood too late that we had prepared to fight a war that no longer existed. Our air defense doctrine was built on Soviet theories developed to counter American bombers in the 1960s and 1970s. Those theories assumed that we would see the enemy coming, that our radars would provide warning time, that we could vector fighters to intercept or launch missiles to engage. Every one of those assumptions proved false. The B-2 demonstrated that technological superiority is not merely an advantage to be overcome through tactics and courage. In some cases, the technological gap becomes so wide that the entire conceptual framework of warfare shifts. We could not see the enemy, we could not track the enemy, we could not engage the enemy. We could only watch our facilities explode and hope that tomorrow night the bombers would strike somewhere else. This is not a situation that can be remedied through better training or improved tactics. It requires a technological response. But developing stealth aircraft requires decades of research and hundreds of billions of dollars in investment. By the time we could field such capabilities, the Americans will have moved to the next generation. This is the reality of warfare between powers with vastly different technological bases. The side with superior technology dictates the terms of engagement. The other side can only hope to survive and adapt. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink, where the weapons you never saw decided the wars you thought you understood. The legacy of the B-2 spirit over Yugoslavia extends into contemporary strategic competition. As the United States, Russia, and China develop hypersonic weapons, directed energy systems, and artificial intelligence-enabled platforms, the fundamental lesson of Operation Allied Force remains relevant. In modern warfare, the ability to operate without being detected provides an overwhelming advantage that cannot be easily countered. The B-2 proved that a platform combining stealth, range, precision, and payload could achieve strategic effects previously requiring entire air forces. It proved that investing in technological superiority, even at extraordinary cost, produces capabilities that adversaries cannot match within operationally relevant timelines. It proved that the future of warfare lies not in massed forces engaging in attrition battles, but in small numbers of highly sophisticated systems operated by highly trained personnel, achieving decisive effects through surprise and precision. These lessons have shaped American defense investment ever since, driving programs like the F-22 and F-35 fighters, the Virginia-class submarines, the new B-21 bomber. They have also shaped adversary responses, driving Chinese and Russian efforts to develop their own stealth platforms and counter-stealth systems, creating a technological competition that defines 21st-century great power rivalry. The B-2 Spirit, that flying wing bomber that Yugoslav air defense commanders never saw coming, remains in service 3 decades after its first flight, a testament to the depth of the technological advantage it embodied. The 20 aircraft remaining in the fleet continue to fly training missions and operational deployments, their existence a constant reminder to potential adversaries that the United States maintains a capability to strike any target anywhere on Earth with minimal warning and negligible risk. When the B-21 Raider enters service in the coming years, it will replace the B-2 not because the older aircraft has become ineffective, but because even greater capabilities are possible with contemporary technology. The B-21 will be more maintainable, more affordable to operate, and produced in larger numbers, but it will carry forward the fundamental concept that the B-2 proved over Yugoslavia, that in the darkness above a battlefield, an invisible weapon that cannot be stopped renders all defenses obsolete, and the nation that owns that technology owns the future of warfare itself.